Okay, good morning already. This is Professor David J. De Los Reyes. Okay, my topic for this session will be a long video format discussion on alternating current circuit. Okay, these are concepts and example problems on alternating current circuits. Okay, let's proceed. My topic for this morning will be alternating current circuit lesson number 10, and the title of the topic will be example of alternating current calculations. Alternating calculations meaning this will now be an illustration of the computation of impedance, current, okay, true power, apparent power, okay, reactive power, okay, and the three calculations or the three methods on how to compute power factor of any alternating current circuit. Okay, let's proceed. So, what we need here is a scientific calculator that involves that got the functions sine, cosine, tangent. Okay, because in the solution of the impedance, we need the so-called conversion from rectangular to polar or polar to rectangular and vice versa. Okay, so actually, what we need is a scientific calculator. Okay, this is the one. It's not so complicated as compared to the other calculators now, but what only we need here is our knowledge of trigonometry plus the sine, cosine, and tangent function for a scientific calculator, plus some other functions. Okay, let's proceed. We are given an impedance, okay? An impedance. So meaning to say, if we try to place this in a rectangular thing, the component of the impedance inside, it got a resistance, it got an inductance, and it got a capacitance. So it seems resistance, inductance, and capacitance are connected in series. But we are not even considering this to be a circuit. It is just a load that is connected to a utility line. Okay? Because there come a time that we will be discussing series circuit and parallel circuit, and for the meantime, this is not even a series circuit. It seems it is a series circuit because the resistance, inductance, and capacitance are connected in series. But this is just a pure impedance, okay? The given parameters are actually the resistance is 10 ohms. The value of inductance designated by L, okay, it is 0.05 capital letter H, meaning Henry. The one who discovered the inductance of the coil, okay? The family name is Henry, that's why it is capital letter H. The value of the capacitance is 1000, okay, microfarad. This farad is also a family name. I think it's the family name of the one who discovered capacitance, right? The applied voltage is 120 volts. It seems we are here in the USA. The utility line voltage here for household are actually, or is actually 120 degrees. There are some 240 or 220, but those are special cases. But mostly the utility voltage coming from the post is actually 120 volts. Okay, if we try to designate the, what do you call this, direction of this, it is an angle 0 degree volts. Okay, you could specify any angle you want, but in the computation of alternating current circuit, okay, we designate that the direction of the utility and voltage is actually at 0 degree. Okay, it's the reference vector. This is. It is a horizontal line. That's why the angle is 0 degree. Okay? The frequency of the power source is 60 hertz. Hertz is also the family name of the one who discovered frequency. Okay, the requirement of the problem is what will be capital letter Z with the subscript T, meaning total impedance. Capital letter I with the subscript T again, meaning the total current drawn by the impedance. Right? Total current. Next will be capital letter T with the subscript T, meaning the total true power. Total true power is the one we are paying to the utility line. The unit is actually watts or kilowatts, okay? Or, kilowatts and watts, okay? Mainly watts is very small, that's only for maybe for cell phones, right? Next one will be capital letter S with the subscript T, meaning the total apparent power. The total power drawn from the utility line. Okay, this is very important because in the computation of the wire size, we need S total. Okay, the total current and power drawn from the utility line. The next one is a capital letter Q with the subscript net, meaning net because there is an X of L and there is an X of C. Okay, so whatever the larger minus the smaller will be Q net. Okay, whichever is larger or smaller. The last one is PF, meaning power factor. So actually, how many unknowns we got? 1, 2, 3, 4, 5, 6. Okay, so maybe if you are in the board exams, they will ask you 6 unknowns for one problem. Okay, the first one is impedance, next one is current, third one is true power, fourth one is apparent power, fifth one is the total reactive power, and the last part is the power factor. Okay, so without knowing your knowledge of what they call this impedance, current, voltage, and other things, you cannot solve this problem. That's why when we started alternating current circuit, okay, we started with the concept. Okay, let's proceed with the solution. If we try to bring out the total impedance, for an impedance that contains R, X of L, and X of C, Z in general, meaning the total impedance, in terms of complex number, this will now be R plus JX of L minus JX of C. Okay, the vector diagram is this one. This is R, this is X of L. No, hold on. This should be, this is not X of L. This should be X net. And X net is actually, what is X net? 16.2. Okay? So for you to not get lost, try to draw the impedance vector diagram. That is the real part is the resistance. The imaginary part comprises of X of L and X of C, but as per our computation, the difference between X of L and X of C is actually 16.2. So this is now the net reactance. And the vector sum of R and X net is actually the value of the total impedance. So if we try to compute for the impedance, it will be R plus Jx of L minus Jx of C. So we must have to compute first the value of X of L and the value of X of C separately. Okay, so let's try to bring out the value of X of L. X of L is actually 2 pi FL. The value of the frequency is 60 Hz. The value of inductance is 0.05 Henries. So using this equation, we substitute 2 pi times 60 times 0.05. What will come out is 18.85 ohms. Okay, X of L. How about the value of X of C? The value of X of C, or the formula on how to compute for the value of X of C, it will be 1 over 2 pi Fc. Okay, where the value of the frequency is again 60 Hz, capacitance is 1000 microfarad. This is 1000. Micro is 10 to the negative 6. It's a very small value, farad. Okay? So using this formula, if we try to substitute, this should be 2 pi times 1000 times 10 to the negative 6. Okay? So in the multiplication of this, it involves negative exponent. So just use your knowledge of algebra or you just use your plain calculator. What will come out will be 2.65 moles. This x of c is smaller than x of L. So supposed to be x net will be the difference 18.85 minus 2.65. It is this portion here. Okay? XL is upward, x of c is downward, but x of L is greater than x of c. So x of L minus x of c is actually 16.2. And the value of R is 10 ohms. Okay? So this is 16.2, this is 10. So in the computation for the impedance, you could bring out, or you can bring out 3 solutions. You can use the Pythagorean theorem, or compute first the angle, okay? This side here over this, press arctangent, it will come out a certain voltage 58.31. And to solve for the magnitude, take the cosine of this, you divide that to the resistance, what will come out should be 19.04 as a first solution. Second solution, take the sine of 58.31. Okay? You divide that to the Q net. What will come out will still be 19.04 ohms. That's the magnitude. This is the value needed in the computation of the total current. This is very important because if you made a mistake on this one, okay, your total current is wrong. And for the third solution, Pythagorean principle, 10 square plus 16.2 square, take the sum, then take the square root, what will come out will be 19.05 ohms. So that is all on your calculator. So if you are on the board exams, you don't have to show it. If it is 10 plus G2, automatic, the magnitude will be 19.04, 58.31 degrees. Meaning to say, you perform the operation ratio 16.2 over 10 on your calculator, raise arctangent, what will come out will be 58.31 degrees. First solution, take the cosine, you divide that to the value 10, it should be 19.04. Take again the sine, you divide that to the 16.2, again, it will be 19.04. Or you can use the Pythagorean, 10 square, 16.2 square, take the sum, then take the square root, what will come out will be 19.05 ohms. Okay, that's the 3 solutions on how to bring out the magnitude of the impedance. Okay, I am telling you all the solutions, but in your solution, when you are on the board exam, just present one solution. Okay, how about the total current? Total current now will be the total voltage over total impedance. Okay, it comes from the equation voltage is equal to current times impedance. So if we try to compute for current, we divide this by Z, so Z cancels, I now will be voltage over Z, or E total over C total. Okay. If we now try to perform what you call this polar division, the applied voltage will be 120. Since it is the reference voltage, the angle should be 0 degrees. Okay, it is horizontal line. So the direction should be 0 degrees. And the value of Z total, again, we will use the value of Z total in polar form. We needed the angle in this solution. So it should be 19.04, angle 58.31 degrees. Okay, we discussed already the method on how to divide two polar equations. You divide the magnitude, that will be the magnitude. And for the angle, it should be the angle of the numerator minus the angle of the denominator. So we bring this 58.31 out. So the total current now in terms of polar form will be 6.3 amperes, negative 58.31 degree amperes. The unit is amperes. It is this. This is the applied voltage, this is the current, and the angle separating them is 58.31 degrees. It's negative. Okay? And the significance of this negative here, it is lagging. The current lags the applied voltage by an angle 58.31 degrees. Okay? Meaning to say, if you see the graph of this voltage and current and the oscilloscope, okay, the voltage was ahead and the current was lag behind by 58.31 degrees. It is this. Okay, that's the total current, 6.3 amperes. Okay, let's try to compute for the total true power, the one we are paying on the utility companies. Okay, it will be like in the DC circuit, power is equal to EI, I square R. Okay, in AC circuit, in the computation of true power, it's still the same. So it will be the square of the current multiplied by R. We are only after the magnitude of true power, so we take only the absolute value of total current and the absolute value of R. 6.3 square times 10, that will be almost 400 watts. 396.9 watts. Okay, this is actually the one we are paying in the utility companies, because if you multiply this 396.9 by how many hours you operated that one, that will be kilowatt hour, and kilowatt hour is actually energy. So that's what we are paying in the utility companies. Okay, but it's a must that you should know how many watts first. Okay, because if you use this one for 24 hours, you multiply this by 24. Okay, that will be your total bill to the utility companies. That's the one you are paying on the utility companies. Okay, what's next? The total apparent power. Total apparent power is the total applied voltage times total current. Just use the absolute value. No need to write this in polar form. It should be 120 times 6.3. S total now will be 756 volt ampere. Okay? That's the total apparent power. The product of voltage times current is volt ampere. That is total apparent power. It is this one. It is this. Right? How about QNet? QNet, because we subtracted already XL and XA and we got XNet. So if we will multiply this one by I square, it will now be the total reactive power consumed by the net reactance. And if we try to bring out the formula, it will be total current square times X net. 6.3 square times 16.2. It is 643. Okay, it is bar. These are here represents reactive volt ampere. So the meaning of bar, okay, this is reactive volt ampere. That's why it is bar. The total apparent power is just volt ampere. And the total true power is just watts. But for QNet, it should be bar, okay, reactive volt ampere. That's why the unit is bars. And if we try to bring out the power triangle, this is the true power, this is the reactive power with the unit bars, and this is the total apparent power with the unit volt ampere. And the angle between this S total and P total is still 58.31 degrees. Okay? So we now know P total, S total, and Q net. So let's now try to compute for the power factor presenting three solutions. This is just for illustration, but if you are on the board exams, just present one solution. Okay? First solution. Power factor will be the ratio of true power over apparent power multiplied by 100%. True power is 396.9 over 756 times 100%. And the power factor is 52.5%. This is too low, okay? Utility companies will get mad at you. They will try to punish you if your power factor is only 52.5%. Meaning it seems the efficiency of your system is 52.5. That's too low. At least you got an 80% maybe. They will not try to punish you with your what you call this payment on the bill, you know. And with the subscript here, lagging. Why lagging? Oh, the current is lagging, right? Right? The applied voltage lags the, the current drawn lags the applied voltage by an angle 58.31. That's why this negative sign here is lagging. So this is lagging. That's why we drew the vector diagram of the voltage and current, so we know if the power factor will become lagging or leading. Okay? Our next solution, it will be the ratio of R over Z. Okay? Because this power triangle actually emanates from this by just multiplying this one by I square, right? I square. So actually, this triangle is actually similar to this. We just remove this I square over here on the impedance. Okay? So actually, the angle is actually, what do you call this, angle between this R and Z represents the power factor also. It will be the ratio 10 over Z. So second solution will be the ratio I square over Z. Okay? Because if we try to multiply this by I square, and again we will multiply this by I square, it seems it is true power and apparent power, right? Right? It's the same as this one. Okay? So supposing you have a problem in which the true power and apparent power are not given, what is only given is R and Z, you could go directly to the ratio of R over Z, and that will now be power factor. So this is 10 over 19.04 times 100%. It is 52.5% and still lagging because the Q net is inductive. If the reactance net is inductive, it is a lagging power factor. Third solution, power factor will be the cosine of the angle between the applied voltage and the current. It is this. It is the cosine. The angle between the voltage and current, the angle, take the cosine of that, and that will still be equal to the power factor. The angle of the voltage is 0 degree, it is our reference vector, and the angle of the current, as per our computation, where is the angle of the current? Negative 58.31 degrees, so this is negative 58.31 degrees. It is actually this one, right? So this will be cosine, open bracket, 0 minus, open quantity minus 58.31 degrees, close quantity, close bracket. Okay? A minus, this will now be plus, right? So cosine of 58.31 degrees, it is still 52.5. Of course, this is multiplied by 100%. Right? 52.5%, this will still be lagging. So in the solution of the power factor, we can present three solutions. Ratio of true power over apparent. Okay, the ratio of R over Z. Actually, this one was derived from this. We just removed the I square over here. And the third solution will be the cosine of the angle between the voltage of the source and the total current drawn. This one, this angle here. Take the cosine of that, and that will still be power factor. It is 52.5% lagging. Okay, that's it, guys. That's how we compute parameters under alternating current circuits. Okay? All the solutions are actually involves complex numbers. So this is now an application or importance of complex numbers, what we have studied under college algebra. But instead of using the designation I, we use the J under the study of alternating current circuit. Okay guys, so for those of you who are planning to take up your electrical engineering course, this is for you guys. If you want to subscribe to my channel is at youtube.com/@proofdavidjdelos. If you want to share it, please click share. Okay, what's my long form video format? I'm discussing concepts in example problems. Okay, good morning from Los Angeles, Professor David J. De Los Reyes.